another example of integrating horizontally with a horizontal element. OneNote notebook. So we will once again draw a horizontal element wherever we so please.
The class schedule is right here under
and
welcome.
And we see that the curve on the right is what color?
We'll be going over each of the days
Red.
in class.
The curve on the right is the black curve.
Like I said,
so we're going to do
Wednesday,
right minus left. So we have to
what we're going to do is have all the homework and quizzes due on Sunday before the exam.
So the area.
So instead of having weekly due dates,
right curve.
Leaving it up to you to pace yourself. Instead of me getting 5 or 6 emails asking for extensions. So it's all going to be due the Sunday right before the exam.
We'll distribute the minus in a minute.
Right. And is there anyone in here that has not used MyMathLab before?
And now we need to know the limits of integration, so we've got to set the curves equal to each other because we need to know what the y coordinates are.
So that is an important page then for our class. We'll stick to that schedule really pretty closely, if not.
We'll set them equal.
So in OneNote, we've got the 2 collaborative spaces. The one here is where if you have questions, this is a great place to post a question.
And then solve for y.
So I just have an example here where I put the problem identification up here at the top. And then ask the question. And let me just jump to my other class for a second because a couple of people have used it. So this is a great way to ask a question because then all of us can see the question, all of us can see, my answer and some tips and whatnot. So it's a pretty convenient place to sort of streamline question answering. You can absolutely use the Ask My Instructor that's in MyMathLab. When you click on that Ask My Instructor, it sends me a photo of the problem you're working on, which is super cool.
2 curves only.
Right, then I can see exactly what the problem is.
We can make up some
and if you do that, that's fine. I'll probably copy and paste it into this section just so that everybody can benefit from the response.
Okay,
so even if you're not asking questions in this area, this collaborative space, you should look at it because there will be questions and answers that are happening in there throughout the semester.
That will act like
when you're in this space, you have full edit rights just like I do. So if you have a question, you can just edit up here. So these blank template pages that I already have up are all full. You can just click Add Page and another one pops up. So you can edit and put whatever you want in there, take photos of your work and upload it. Down at the bottom, I see all of you, but in your OneNote accounts, you're just going to see yourself. Then we're going to distribute the minus sign. So that's going to be a collaborative space just between me and you individually. So no one else can see.
3y squared.
This space up here is totally public. We all get to see it, and I'll get to write in it. Down here, if I just go to Daniel,
minus 3y.
Under Worksheet, Chapter 6, this is going to be that second component of homework. There will be 4 of these worksheets. They will be a little bit more conceptually based instead of the skill and drill that MyMathLab has. So we'll have 4 of those. Chapter 6 and then 3 other chapters. The main chapters that we're doing, 6, 8, 10, and 11. Those are the main chapters. And you can, if you have a tablet device, you can write right in here. You can type. You can do whatever. You can take photos and insert very easily, insert pictures, insert PDFs, insert whatever.
Plugging
so
in the
it's
2
pretty easy interface to add your own content to it. And so that will also be due that Sunday right before the exam. So does that make sense to everybody? Yeah, Roberto?
Would we be able to have
then we're going to subtract off
on those ones, the same as the homework?
No, these you're just going to work on just one try.
What?
Okay.
Yeah. So if you have questions and you're not 100% sure, you can ask.
-3 here.
Yeah, it's not. The main point is for you to think about how to do these and to ask. And I'm not grading them. It is graded for correctness, but I will be super lenient on that. If you're close.
Plug in the -3 here. We can
but you can ask questions on these in class. We're going to do examples that are very similar.
Okay to everyone.
But all of them are show or set up, but don't integrate. So it's not focused so much on the skill.
We've definitely seen better.
More focused on the concept.
So
how to find area and how to find volume.
Okay,
so each one of you will have that little collaborative space down below.
And then let's combine these
Any
two.
questions thus far?
27. That's going to have a minus in front of it.
Daniel.
Plus-
Oh, okay. Oh, I think I just opened your account, actually.
You did.
And say you go by Danny?
Dan.
Dan, gotcha.
So then we get -5, get a common denominator of 2, so -10 over 2.
All right, so anything else that,
Right here,
Just have
So-
Sure.
plugging in.
Oh, homework questions from 6-1?
Yes.
I don't know.
Let's wait a
Great
minute to, let's, I want to get
We plug in
started
-3
on the
right
6-2
here,
stuff,
becomes
just because we didn't
positive,
get
but
quite
it's
as far
only
as we
cubed, so it's
should
27.
have.
Thank you.
So let's get a little bit into
And then
6-2.
27 minus 54 is
and then,
-27, but that might
maybe what
make
we'll
that
do
a-
is set those up during the break or something, so we can kind of double dip. We'll get those
Thank you for
answered
catching that.
in due time.
All right, so then what's that? 49.
All right, so we are in 6-2. We're starting 6-2 today. So we are going to find area between curves. That's going to be our first
So
task.
98,
And
99, 120.
one nice thing in this class is that we are not going to be doing Riemann sums.
25 halves.
So we learned in Calc 1 all about Riemann sums, and I know some of you are very sad not to find left endpoints and right endpoints
Cal
and
part
interval
seems so
widths
much
and all those things. So if you
Fractions.
really want to do some with a Riemann sum and a limit, you
All right,
can.
questions on any
But in this
step?
class, we mostly are just going to wave our hands and say, poof. So here is our first Riemann sum motivated topic, and that is the
Here is
area
a
between these two
region
curves.
that
We've got
is
this upper
a
curve and a
region
lower
that
curve.
could be
And whenever we're finding area, we're
integrated
thinking of
either
subdividing our
You could
region
use a
into
horizontal
area.
or a vertical.
Region is a space
Now, when we
in two
look at
dimensions.
it, both functions
So we're going to
are
subdivide our
presented as
region into
y values.
rectangles.
So it
In
makes more
practice,
sense
we
to
think
just
about
go ahead and
subdividing
go with
into
convertible elements.
rectangles that
That's
have
how it's
equal
presented
width.
to us, and we don't have to do
And
the extra work.
You don't actually have to have them have equal
But
width.
you could use either.
We don't
Either will
need
work
to
fine.
focus on that.
So let's
And
go
we all know how to
ahead
find the
and
area of a rectangle, base times
say that
height.
the area is equal to
And so the
integral
idea here
of
is
upper
that we
minus
set
lower.
up this
So the
Riemann
upper
sum.
curve is
The Riemann
red
sum
one.
gives us an
Lower
approximation
curve
for
is
the area.
black one.
Take our region, build a bunch of rectangles, add up the areas of
And
all
our
those
limits of
rectangles.
integration
That's
are
an
0 and
approximation
1.
to the area of the region. And then the magic
Kind of see by
happens
inspection.
when we take the limit of a Riemann sum.
If you don't see it by
So
inspection,
the main
just set
thing
them
in Calc
to each
1
other
that
and
you
solve.
walked away with is that the limit of a Riemann sum is a,
Square root equation.
definite
What do you do to
integral.
both sides when you have a square
that
root?
is what the limit of a Riemann sum gives you. Gives you the definite integral. The definite integral,
So we'll
shaped like an S,
Yeah.
for sum.
If we
Because you're
square
summing up
both sides,
rectangles.
we end up with this.
When you see the integral symbol, that's what you should be
And
thinking.
then
You are summing up little rectangles.
everything to one side.
The
back.
f minus g, that is the height of a rectangle, of our representative rectangle.
Don't divide.
So this is
Don't
representing
divide by
height
variable.
of a rectangle, and the dx
Zero.
is representing the width of a rectangle. And so whenever we do an integration, we are going to draw
So
an
we see that
integration
places
element.
of intersection
And
are
we are going to
x
imagine
zero
the
and
height
x
and the width
one.
of that integration element.
So, that tells
So for
us that
example,
our
right
limits of
here,
integration are going to be 0 to
We've got these two curves,
the
and I'm going to draw this
interval on which
integration
this
element,
region lives is
and I'm
0.
drawing it at a random x.
And
You
we
don't
can
have to
integrate
label it at a
this
random
term
x,
easily
but
with
it
the
doesn't
power
hurt.
of. So this is x.
So that's the
halves,
integration
that becomes
element at
x to the
x.
3 halves.
You're imagining it as a little thin
And that
rectangle.
becomes x to the
You're
4.
imagining this as the height of the rectangle right here. The width of the rectangle is just
2/3
dx.
minus a fourth.
So you're thinking about
Common
area of a
denominator,
rectangle
12.
here. We need to calculate the height
8 minus
and then multiply by the thickness, which is dx. So that's going to be our visualization for finding the area between two curves.
our result.
And you should know by now, if you're on a vertical axis and you want the distance between 2 points, you take the upper coordinate and subtract off the lower
Any
coordinate.
issues?
If you're on a horizontal line and you want the distance, you take the right coordinate and subtract off the left coordinate.
Okay.
Right? That makes sense? That gives you distance. Right minus left, or upper minus lower if it's vertical. So when we look in here,
Any
this
questions?
setup here, we have two functions.
You have a question?
So this element, you could imagine drawing it wherever you want, right? That element just has to connect the two curves.
You have a homework question? What homework question?
So if we want the length of this element, we're going to create the length of this element or the height of this element as a function of
We
x.
will get to it.
Because as you slide that element throughout the region, the height's changing. So the height's a function of where you are on the x-axis. So it's going to be a function of x.
Curves. The
Now,
first one
the
is easily
next thing we need to know
sine of x.
is where
Sine of x we
are
know
these
has
intersection
key
points?
there,
because
key
that
there,
dictates
key
the
there.
width of the interval. That tells us our
There's
start
sine.
point and our terminal point. So
Yeah.
we need to know where those two curves meet. And the way we figure out where curves meet, we set them equal to each other, and then we will
for any graph
solve
that's
for
not a
x.
basic graph.
So we're going to set
sure.
these two curves equal
There's
to
one
each other
graph
and try to figure out what their
that
common
was like something
y
for
values are. So
something-
we
one
set
of
the
its
y
squared, four
values
minus x
equal to
squared
each
or
other, and now
something,
we're going to find the x values that give us those common y values.
Should be able to graph like sine these
So
things.
this one will be probably easier to move everything to the right.
Okay, what kind of curve is that second one?
And classic equation, nonlinear. Anytime we have a nonlinear, everything goes to one side and you factor. Right, that's our procedure.
You can say it.
for solving a nonlinear
Right, it's
equation.
an x squared, so it's going
Everything to one side and factor.
And we know that parabola, and is it going to open up or down?
And we can factor out a 2x, that's going to be our
We know it's a parabola
GCF, so we're
opening
going to
up.
have x minus
And now we don't have to
3.
get super precise with it.
And that tells
But when
us,
we look at it in this
that
factored
x is
form,
either
we see
0 or
that the
3.
zeros are 0 and pi.
so those are the two x values of the two
and we know that it
intersection
opens up,
points.
so we know the vertex
we now
is in the middle
know
of those two.
that we
so we
have
don't
this point
really
right
care how far
here,
down it goes.
which is
We
0,
can find out if we
0,
wanted to.
and this
But we don't
point right
have to.
here
This
is
is
3
maybe
comma
y equals
whatever. We
x
don't really
squared
have to
minus
find the y value, but it's easy enough to find it. Plug the 3 into
So we
either
just
one
wanna
of the
draw the
functions.
graph
3 squared is
close enough
9,
that
9
we
minus
know
6.
What's on top, what's down below.
So those are our two intersection points.
Yep, the vertex is going to be
All
right
right,
there.
so now we see
we don't have to
that there
plug
are
in pi over two and
rectangles,
figure out
vertical
what the exact y
rectangles
value is.
throughout the
We don't have to do
interval
that.
from x equals 0 to x equals 3.
So this tells us that
So
if
now we want
want
to sum them all up. We want to add up all those
that
rectangles.
Our area.
So we are going to add up. So the area will be the sum of the
So
rectangles
you're telling
from
us that
0
we're
to
gonna
3. And the area of a rectangle
and then
is the height
curve on
times the
top,
width.
sine of
So the
x.
height is the
And the curve
upper
down below is
function
that one.
minus the
Subtract
lower
off that
function.
one.
So upper function is negative x squared plus 4x.
That will be our setup.
And then we subtract off the lower function. Lower function is x squared minus 2x. Good? So there is the height of the rectangle at x. Now we multiply it by the width.
And we can go ahead and distribute the minus and integrate at the
Collect
same time.
like
So
terms
integral of sine
and
is minus
integrate.
cosine. And then minus.
So
x
distributing the
cubed divided by
minus, we will
3
end up with negative 2x squared.
plus pi.
And then we're going to have
x
4x
equals
plus
2,
2x, which is 6x. And then we can go ahead and use the power rule to integrate this.
First, we'll plug
So
in the
power
upper
rule,
limit. Plug in the pi
Add 1
value.
to the exponent,
So
divide by the new
cosine pi is
exponent.
negative 1.
Anytime you have a power of x, that's how we'll integrate it.
Pi
Add 1 to the exponent,
3
divide by the new exponent.
plus pi cubed over 2.
And then we plug in our limits of integration and take the difference.
Minus
The
antiderivative
lower limit of
0.
integration is the 0. That
This
is
part of the
not going to
antiderivative
contribute
of 0
anything.
is 0. So we have minus,
just a
minus,
decoration.
which is plus cosine of
contribute
0. Cosine of 0.
Plugging in the 3 here, we get 3 times 3, which is 9. One of the 3's cancel, so we get negative 18. And then 9 times 3 is 27.
The limits of integration are given to us. So they tell us
That
that we're
will
going to
be
go
our
between
area.
0 and pi.
The area between those two curves.
Math is a visual activity.
Any
So then
questions?
we're going to end up with 2. And if we get a common denominator of
Can you go back
6
up?
for
Sure.
When you like
this-
subtracted
these
the
two terms
equations,
here,
so how do you know
we're going to have
is
minus
it the x squared minus 2x
pi
on the bottom
cubed
because
plus
it's like
3
the
pi
one
cubed,
below?
which is
Like is
1
that just
pi.
Exactly. That's it's as simple as what you just said. It's the one below.
okay?
So it's always the upper function minus the lower function. Yep.
No.
It's always top minus bottom for vertical and right minus left for horizontal.
That's pi.
And then for the x
points? Like, what if it wasn't 0, 0, and you would know like the 0
There
is
we go.
obviously gonna go. Like, do you plug in both the 0 and the 3
And
equations?
isn't
Or?
it
if you plug it, it will give you the same answer regardless of which equation, because what we did was say, hey, when are these two functions sharing a y value?
It's time to
So
go to
that
3
when
dimensions.
we set the y values equal to each other, we end up with the,
like we
with the
live
x
in
values
3
that
dimensions.
give us those common y values.
Just
So this says that x equals 0, the two functions have a common y value. At x equals 3, they have a common y value. And to find that common y value, you can plug this
Okay,
0
so-
into this function or this function, plug this 3 into this function and this function.
Okay, so now we are going
So we'll
to
give you the same
extend the ideas of integration to find volumes. And so our
Go down or up?
strategy is very similar. We're going to use Riemann sums, at least in the background. And the idea is that
Okay,
we are
so
going to have a solid object. which
what
could be
we are
created
doing
in a couple
here
of different ways.
is integrating with respect to x.
When we just
So
have
we're
a solid object, we
integrating
can take
regions where you can
take
draw a
cross-section.
vertical element.
So a
Soon we will see
cross-section
some
is gonna
regions
be
you can't draw a vertical
you
element, you
know,
have to
width.
integrate
It's
with
gonna
respect
be
to y
infinitesimally
instead of
thin.
with respect to x.
It's not going to be a little volume.
First, we're going to go through the integrations with
Cross
respect
section
to
is
x.
two-dimensional.
So this is another one. This one you can draw
But
a
then,
vertical element, and a
Just
vertical
like
element
with the element,
will
we do a
connect
vertical
an
element
upper
at
curve
that
to a
height,
lower
and we
curve.
sort of puff
This
it
will
up
be
to
a
have
random
thickness,
vertical
which is
element at
dx.
an arbitrary
Same
x.
idea here. If we take our cross section and then we add a little
The upper
thickness, then we're
curve
gonna
is
call
just
it a
the
slice.
x-axis in this
So
case.
cross section is two-dimensional.
What's the
a
equation of the
slice is
x-axis?
three-dimensional, but very
So
thin.
just y equals
So we're
0.
gonna call
So that is the
this
upper curve.
slice.
That is the upper y
We're
value.
going to say that it has cross-sectional area.
The lower
whatever
y
area
value
over
is that
here,
other
and
thing.
The thickness is dx. And you can see
So same idea as the
that if
previous
you
one.
Subdivide your
We
region
imagine
into
all
a
these
bunch of those little
rectangles stacked
slices,
sideways.
it's going to approximate the
We
volume.
want to add them all up.
So
So
the
the
volume
area
of that slice
is going
the
to be
cross-sectional
equal
area
to
times the thickness.
the
This
integral.
in
We don't know our
here
limits yet. We'll
is
find
the
them in a
volume of
second.
the slice.
The upper curve minus the lower curve. So the upper
And then
curve
we
in
add
this
them up
case
and we
is
get
0.
approximation.
That's the y value for
we
the upper
learned in
curve.
Calc 1.
The y value for the lower curve is this x
So
expression.
as
So
you
we're gonna
let
subtract
n
it
go
off.
to infinity,
Let's go ahead and distribute
your
the sign. It's
approximations
going to
get
be a
better
little
and
bit
better and
easier
better,
to deal with if
and then
we
when you
have it
take the limit,
distributed. So
the limit of your Riemann sum becomes a definite integral.
that's what
And
we're
we
dealing
know
with.
how to deal with definite integrals. Definite integrals are very manageable.
Now let's find our
That
limits
is
of
the
integration.
integral that
So our
we're
limits of
gonna use.
integration,
All we have to do is
at least
take
according to the
cross-section
picture,
area.
it seems pretty unlikely that this is
So there are
not
two
0,
ways to
0.
think about this integral.
And we've got to
You can
find
think
out.
about
So we need to set the two curves equal
conceptually
to
that
each
the
other.
integral of area
In other
is
words,
volume.
we are going to
Think of it
just
kind of that
figure
way.
out
Just
what
like what we just did on the
cosine
previous
x
slides,
minus
we
2
integrated length
multiplied by
to get
sine of
area.
x
Right, our
equals when it's equal to 0.
functions, we're measuring the length from the x-axis up to the curve. If you integrate length, you will get area.
Rewarding me.
If you integrate area, you will get volume.
And this
So it
tells
kind of
us that
parallels
cosine of x
the
is
acceleration,
equal to 2
velocity,
or sine of x is
position
equal to
argument,
0.
where you have two derivatives and two integrals that line up to go from one direction to the other. So, what
Where is
the
cosine of x
area
equal
of
to
a
2?
circle? What is the derivative
When is
of
cosine equal
this
to
with
2?
respect to r?
Never, right?
Voila!
Never, never.
Take the area of a circle,
question.
take its derivative, you get the perimeter.
So
You get
cosine
the
is never equal to
Take
2.
the derivative of area.
Cosine wiggles around between -1 and 1. It's never up there in 2.
What?
So it's got no solution there.
So,
Sine of x is equal to 0.
same thing holds
Anytime we have one of
for
these basic
volume
trig
and surface
equations,
area.
it's usually best to draw
You,
it in
most
a
of us
circle.
don't know the surface
And
area of
is
a
the
sphere.
sign
But many
corresponding
of us
to the
probably
y
remember
value or the
volume
x
of a
value
sphere.
along the unit circle?
Well,
Y value,
Sphere,
alphabetical
pi
order.
cubed.
C before S, X before Y.
Never seen
Cosine
that
before sine, X before Y.
How many dimensions
So
do you
the
live in?
places on the unit circle that we're looking at are right here.
So what is the derivative of that with respect to
So
r?
0 and pi are the first two. So 0 and then
differentiating
pi
that
and
with
then
respect
2
to r
pi,
gives you the surface
or
area of the
also
sphere.
negative pi, negative
So
2
that
pi.
connection,
But when we
where
look
you
here, the
integrate
x-axis is
length
measuring the
to area,
angle.
integrate area to get
So we
volume,
want
we're
the
gonna see
first
that
two.
a
We
lot.
want x equals 0 and x
You
equals
can
pi.
also think of
We
this
want those first
less
two.
conceptually, and you can think of it more mechanically, in that this is a slice and the integral is just summing up all
So
the
now we
slices
know our
to get
limits
the
of
total
integration,
volume.
0 to
A slice
pi.
is a mini volume. And the integral is just summing them up to get the total volume. So
And
you
we
think
get
of
to
it
do
either
a
way,
little-
conceptually or more mechanical. So here we go.
So another thing
Got
you
this
learned
solid
in
object.
Calc 1
And this solid
is that
object
the
is created
integral symbol
geometrically. They say start
will
with the curve y
distribute.
equals the square root of 3 minus
So
x.
you could write
Which
this
is that curve
as
right
two
there.
separate
And
integrals.
look at the interval 0 to 2.
Distributes over pluses and
So
minuses.
here is a region in the xy plane. And that second integral
is easy
that
enough.
is the base
That second
of the
integral,
solid. So it's in the xy
we know an
plane, the solid is
antiderivative for
sitting on top
sine
of that.
instantly.
So the xy
That first
plane
integral is a
region
little more
the base
complicated.
of the solid, and then the solid sits right on it, right?
That first integral,
So what they're
we
gonna
have
do
two ways that we
is
could get
tell
at
us
it.
How?
Anyone
to
have
make
any
it solve.
ideas for the ways that we could
First
get at
thing
it?
is that when we talk about cross sections, they are always perpendicular to the base of the solid. We're not dealing with any sort of weird angles
One
coming
way
into the base of the solid.
Is to
We're not dealing with any sort of
recall
weird tilted prism
from,
type things.
let me point out in our
Base.
OneNote
Cross section.
notebook here under
Cross
handouts,
sections, what we
there's a
are
bunch
going to
of
figure out
stuff.
are the cross sections
And there is,
parallel to the
in
x-axis,
particular,
or are they perpendicular to
trigonometric
the x-axis?
identities.
Those are our two choices.
And we have a double angle
Parallel to
identity,
x,
which would take
perpendicular to
the
x.
product of sine and
Which,
cosine and turn it into a
the other
single
side of the coin, you
function,
could say parallel
which
to
would
y,
then be
perpendicular to
integral.
y. It doesn't matter. It's
So
one or
that's
the
one
other.
way.
It's going to be with respect
Use
to one
trig
of the
identity.
axes. But
Here's some basic
the
integrals
cross
that you
sections
should
are always
see
going to
in
sit
Calc
upright,
1.
perpendicular
So
to the base.
different handouts there that you.
So this says
one
the cross
option.
sections
I'm not going to
are
opt for that
perpendicular
option.
to the x-axis, and they are.
There was a
square.
technique you learned at the
So
last.
this is why I
the
drew
last
this
couple weeks of
element
Calc 1.
here,
Integration by.
vertically, because it says
use substitution.
perpendicular to the x-axis.
So you sub if you have
That
an
element is
integrand
perpendicular to
and
the
it doesn't
x-axis.
have an immediate
And then we
antiderivative.
imagine these
The first
squares are
technique
coming
you should
straight out of
consider
the
is
board.
use substitution.
So whatever this
And
distance
use
is
substitution
right
will
here,
work whenever you let
that
u be
distance is going to then
part
tell
of
us
the
how far out of the
integrand
board
and
we're
its
coming,
derivative
because we're
is the
building
other
a square.
part of the integrand.
Question. And we could go either way here.
If we let u be sine, its
Yeah,
derivative is
exactly. One or
cosine,
the other.
and then this minus sign would
So
get
if they would
factored
have
out
said
to
that
the
we were going to
front,
draw
and we could convert it over to u.
cross sections that were parallel
Or we
to
could
the
say, hey,
x-axis,
what
we
about
would
if we
draw
let
that.
u be cosine, then its derivative is minus sine.
So-
Minus sine is right there, and
What's
that
the
will take
area
up the whole integrand, and we won't have to worry about factoring out a minus
Even
sign.
more simply,
Doesn't matter though. U equals one or the other will work in this case.
Square. So
So let's go ahead and do
the
that.
area of our
So let's suppose
square-
we let u be cosine of x. The derivative of
Here's the
cosine
base
is
of the
minus
square.
sine of x.
Using the word base, you have to be careful. There's
There
the
would
base
be
of
our
the
substitution.
solid, and then there's the base of the square. We could call this one side of the square. And then the height of the square, same thing.
So substituting,
So
the
that
cosine is
the area
becoming
of
a
the
u,
square at x.
and minus sine of x dx is becoming
So if you
du.
plug in x equals 2, you
Yeah.
will get that this square that's coming out of the board right here has an area of 1. 3 minus 2 is 1.
Limits of
Or
integration.
you plug the 2 in here and see that, oh, the base of the square
We have
has
two
rank
choices.
1. That means the
We
height of the square is
could
also
say,
1, so
let's just integrate with respect to u, and then go
If
back
you
to
look
x
here
and
at
use the x
0,
limits of integration.
the
That's
area of
totally
the
fine.
square is going to be
Or we could use
3.
this equation right here. That
What are the
equation
dimensions
tells
for the
us
square
how many
0?
u's an x is worth, or how many x's a u is worth. It tells us how to go back and forth between x's and u's.
of that square?
So that, if that equation is simple, if it's easy to plug these x values in here and get u values,
the base,
just
if
do
the
it.
dimensions were 3.
Either way is
3
totally
times 3
fine,
would
same
give you an
answer,
area of
both
9.
ways. Let's do
Root 3 and
the
root
conversion
3.
here. Let's convert
So
to
if we
u
look
limits.
here at our curve,
So this is a
the curve
dx,
here, if we
which
plug
tells
in
us that
0,
these are
we'll get
x
that this y
values.
value is root
When the
3
x value is
right there.
0,
That's
cosine
root
of
3,
0 is
which means then we come out of the board right
1.
also.
So then the corresponding
square will
u
have
value
size
is
root 3.
1. When x is pi, we plug in pi right
So now
there.
to get to the volume,
Cosine of pi is negative 1. So that goes
So volume
right there.
is the integral of area.
Come over here now.
And
What's the
they tell us
antiderivative for sine?
that we are looking on the interval 0 to 2.
Negative
Tell us
cosine.
that
So we're gonna, and the 2 just factors out to the front. Upper limit 2, lower limit 0. Constants just factor to the front. Yeah. So now we have this.
Is it always like left to right?
We integrate u and get u squared divided by 2.
So this
or
element
1/2
right
u
here
squared, however you prefer to write
It is
it.
perpendicular to the x interval, so that means we're using x's. It's a dx.
And over
The thickness of
here,
that is dx, which tells you your limits are coming
minus
from
2,
x.
let's go ahead and plug
So then
in
it's
the
always
limits of
left to
integration.
right.
So the minus 2 can be out in front, and then we're going to plug in the limits of integration
And
into
that's pretty easy.
cosine,
Integral.
and then take the difference, starting with cosine pi.
Is there no problem to doing the integration like with u to the left and x to the right? That's fine.
Totally fine, yeah.
So that'll be
Because
cool.
this symbol here indicates that we're done. As soon as we get to that du, we're done. And that's one term, and then this begins a
3D is
second
not
term.
that bad.
Yeah. So cosine pi, -1. And then we
Internal
subtract
arguments.
off.
Ryan Jones.
So I'm plugging in just the cosine, minus 2 is factored out.
All right.
Plugging in the pi gives -1, then we subtract off the value cosine of 0, that's 1.
So with this next one,
And then
the
over
way
here-
the solid is going to be created is by.
What do we get here?
Oh, hold on, maybe I'm misspeaking. I got distracted.
The 1/2 is out in front.
So one other way
Plug
that
in
we're
the
going to create
-1, we
solids,
get
we do it
1, then we
geometrically.
subtract off what we get with the lower limit.
Cross sections are going to be squares or rectangles or
And
triangles
this all
or
becomes plus
semicircles
4.
or something. We can also do a
1
rotation.
minus 1 is 0.
So this one is,
Four
okay, so this is a
the
rotation. So here we've got a
area.
region and we're going to rotate it around the x-axis and it's going to create cross sections that are disks. If your region is touching the axis of rotation, and we take this vertical element here, it
Any
rotates around the
questions
x-axis,
for
it's going
Berto?
to create a
You want to
disk.
plug back in your
And that's an easy geometric shape to find.
Well, we're plugging in our u values right here.
This is a
So you,
is a
if
nice
we
special
chose
case
to not put
where we have
u
cross
limits
sections that are
here,
disks.
we would come
So this
here
tells
and
us
we don't have any
That
limits
our
here.
curve that we're rotating
Then we would
is
plug
root
that
x.
back in, and then we could
That's
put x
going to
limits.
act like the radius
So you could do either.
of this disk over
You can
here.
convert to u limits and evaluate
What
with
is
the
the
u
area
limits,
of a
or
disk?
wait and go back to x.
Okay, that makes sense.
Pi r
So
squared.
limits are like
Radius
negative
is
one,
root
those are
cosine.
Is the limits of cosine of x.
Those are the limits. So those are the u values that correspond to the
So
x
voila.
values.
That
The u values are
formula right
found
there,
by
that
plugging in the
function
x values
is
into
going to
cosine
give
x.
us the area.
So
of
this
the
is
disk
cosine of
at
0,
x.
the lower limit, cosine of 0.
So when we look at
And then
this
the upper limit is cosine
solid
of pi.
object here,
Okay.
we can imagine all these
So we
disks
can always
that are,
convert to u
that are
if
stacked
we
next
have
to
that
each other.
equation.
The disk here at the end should have an area of what? 0. Let's check. If we plug in pi over
If
2, cosine of pi
this
over 2 is
equation
0. So yeah,
Isn't really
that works,
easy
right?
to convert
the
over to
biggest
u's,
disk is going
then
to
it
be the
might
one
be
right
better
here on
just
the
to wait
left,
and go
where
back
the
to x
radius
in the
is
end.
1.
So
The
I
area
would
of a disk
almost
is
always
radius
convert
1
if
and pi
the
times
equation
1
is simple
pi.
enough.
So let's check.
But if there's,
Plug in
there's
0
inverse trig
in our
functions or
area
things
formula,
that
we
just
should
seem a
get
little
pi,
more
and sure
complicated,
enough,
it
we
might
get
just be
this
better to
cosine
wait
of
and go
0.
back to x.
So that is our area
there will be
formula for the
times
disk
where-
at x.
And there'll be lots of
Now,
times
if we
actually
want to
it's
find the
possible.
volume
So let's
of this
just wait
solid
and go back
object,
to x.
we will integrate from
But there's
0
no
to
rule.
pi over
Both
2.
will work. Both will definitely
The
work.
cross-sectional area function.
All right, let's try another one. So here we have two trig curves. One of the nice things about Calc 2 is all the
Antiderivative
things
for
that you
cosine
didn't
is
quite get in college algebra and trigonometry and Calc 1, all those things are going to come into play in Calc 2. There is a ton of algebra,
Once again,
there's
the
a ton
lower
of
limit's
trig.
not going to do much. Sine
Calc
0
1,
is
you
0,
don't
so
use a
we
lot of
ignore it.
trig. Calc 1, you learn some basic derivatives, you do
And
some unit
sine
circle
of pi
stuff.
over
but
2.
not- We do unit circle stuff every week.
1,
So you want to go
that is our volume.
into our OneNote
The
thing
volume of
and
that
go
solid object
over
created by
to the
rotation.
handouts again. And there are unit circles here for you to practice. You can
Can you
print
go
out
ahead
some
on how we got
blank
the
8s and 12s.
So the
and,
radius
practice
is the
them.
function.
You really want to
So
have
the
those
radius, does
down
that make
because
sense?
we use
Why-
so
yeah,
much
it just
trig. in
doesn't
here.
look like it's like pointing.
The
towards
identities
so
in
I
Calc
think
1 that
the
you use for
focus
trig,
is sure.
not a lot.
So this function right
Here we are
is
gonna use
measuring the
identity-
distance
trig identities
from
almost
the
every
x-axis up to the curve.
Lots of trig.
And then
Calc
that
2 and Calc
element
3.
right there, when it rotates around
Tons
the
and tons
x-axis,
of
it's
trig.
like a
So this is a
spoke.
great opportunity
And it's
to
gonna create a
really
disc.
nail your trig down.
And
so the radius by definition is going to be the value of that function. We will talk about the identities that you need for each particular test. Each test will have a different subset, but you will need to know them. The final you can have a note card, but the individual exams you can't.
Can we have a
No.
calculator on the whole test?
Not if you want to pass. You can have a calculator, but you can't have a graphing calculator. No, you won't have to graph anything, so that will help. That will help in lots of ways. Some of these things in 3D in some ways that I don't even want to know. So let's go ahead and take a look at this. In Calc 3, you will need to be able to graph basic trig functions, basic algebraic expressions. Okay, so let's take a look at graph when you're trying to find area is super helpful. When you look at a graph, this is going to be described geometrically. Which one's above? So this one is not going to be a solid that's generated by rotation. So you definitely want to practice trying to do your graphs by hand. So what they do is they tell us the base of the we're looking at cosine and sine, and then they tell us if we graph them, we know that sine has. So here they say we've got 2 points right on the x-axis, and then we're going to create. And then sine starts up and then down over here. So there's sine square. Whereas cosine, we know that it starts up and it finishes up. And it's down right in the middle. So these are the 5 key points for cosine. Sometimes it's we just connect the dots. See what the solid looks like even if you can't draw it. And then we have to figure out, okay, well there's these 2 intersection points. These days are pretty good. And then we look up here and it says pi over 4 and 5 pi over 4. And then hopefully you're thinking about your unit circle. You're saying, oh, wait a minute, on the unit circle, aren't those 2 points, or those 2 angles, pi over 4 and 5 pi over 4? Those are the angles where the sine and cosine values match. Right, in quadrant 1, sine and cosine are both root 2 over 2. In quadrant 3, they're both negative root 2 over 2. So that is where these 2 curves are the same. Squares, you can slide this. So they have actually given us the x values of these 2 intersection points right away. Down here. So the opacity, so nice. You can sort of turn it into a wire. All right, frame. So now we're drawing our vertical element. That's our little rectangle, representative rectangle. And that rectangle can be drawn anywhere in the region. And it makes sense to draw a vertical element because the upper curve is always the green, is always the blue curve, and the lower curve is always the red curve. So that's when you use a vertical element, when you have a consistent upper curve and a consistent lower curve. You would not draw a horizontal element. Well, actually, in this case, it almost looks like you could. But if you look very carefully right here, maybe it should be. That horizontal element would have red curve and red curve, which you do not want. Because up here you have red curve and blue curve. So it's different. You draw the element in a way that you have consistency above and below, or consistency on the right and left. The area of so this you would not want to use a horizontal element. So we definitely are going with our vertical element, and our area. What is one side length? Will be the integral from pi over 4 to 5 pi over 4. And then we want to do the height of the rectangle. There is an x in it. X squared. So what is the upper curve here? So if you look at height of a rectangle, that's a vertical distance. Height is upper minus lower. Down here, so we want to take the blue curve and subtract off the red curve. The blue curve is sine. So we're going to do sine. So we're looking minus cosine. Right. So that is the height of the rectangle. So the upper curve is this one. The thickness of the rectangle at x, and the lower width of the rectangle at x, up, dx. So it's going to be upper minus lower. So that'll find the area between those two curves. So the upper one is 2 minus x squared. And then we subtract off the lower one, so we get 2 minus. And this one's not too bad because both those functions have antiderivatives that we know, which is going to antiderivative for sine side of a square. Negative cosine 2 minus 2x squared. Antiderivative for negative cosine. But then we square it. Negative sine. So the area of a square, base times height, both base and height are 2 minus. This will go from pi over 4 to 5 pi over 4. Then we FOIL this out. And now we just have to plug in those values. So like we mentioned with this picture of the unit circle here, at 5 pi over 4, both the cosine
As a
and the
function
sine
of
are
x.
negative root
So
2
if you
over 2.
slide through that
If
x
you multiply them
interval,
both by
the square
negative
that
1,
sits above it
you end up
has
with
that
root 2
area.
over 2 plus root 2 over 2.
Yeah.
Where does the second 2 come in? Because it's 2 minus 2x squared?
So
And
the
now we
upper
subtract
curve
off
is
the
so
antiderivative
one side of the square
at pi over 4.
I'm going to call it L.
Well, when we subtract off this expression,
So it's gonna be
that
2
minus
minus x
distributes and makes
squared.
both of those
This
positive
upper curve, and then we have to subtract
sine and
off the lower
cosine
curve, which is x squared.
of pi over
That makes
4
sense.
are again root 2 over 2.
So that'll
You
be
end up with
one
that.
side of the square.
Where does the square come from?
So add all
Because we're
these
finding
together,
the
and you
area
end up with 2
of
root
the
2.
square. So it's going to be that times that.
Oh, I see. I see.
The area. And then we just integrate that function and we get the volume. The volume will be the integral of this. And then we just have to find our limits of integration. All right, so let's go to the next one.
And how do
I'll
we find the
get
limits of
you
integration?
through
We're
the
gonna set the two
graphing
curves
phase, and I'll let you do the
equal to
integration
each other.
part. So we're going
we
to
got
graph
x
these two
squared
functions.
is
So it says the
lower
region
curve,
in
the upper
quadrant
curve is
1
minus x squared.
bounded by these curves.
So we end up
So,
with 2x squared.
Y equals 4. We know that
Divide
that's
up
just a
2.
horizontal line.
We get
So
x
y
squared
equals
is equal
4,
to 1,
something like
so
that.
x is plus or minus 1.
Y equals 2/3. X to the 2/3. Y equals x to
minus
the
1 to
2/3. Fractional
So you could go 0 to 1 and
exponent.
double it.
You've done the square root function a bazillion times. Anytime you have x to a fractional
symmetry?
power, 1/3, 2/3, 4/5, 7/9,
Having a limit of integration
11/13,
zero
doesn't
is
matter. If it's a
always
fractional
nice. It's a lot
exponent,
easier to plug in
positive
zero.
fractional exponent,
So
you
we
always
could
are going to get this bird wing looking thing.
Do that.
It's always going to do something like that.
But
It's
we
going
can
to
only
look a
do
lot
that
like a root. And we don't care how
because
steep
both
it
these
is. All we
curves are
care is the
symmetric
general
about the
shape.
y-axis.
Looks kind of like a bird's wing.
Y
Anytime we
equals
have x
squared,
raised to a
y-axis.
fractional exponent,
Y equals 2
if it's
minus
negative,
x
things are a
squared.
little different. But
Also
and
symmetric.
if the numerator is positive, excuse me, if the numerator is
Say again?
even, you know, if you look to the left of the y-axis,
So
things
let's
will look a
integrate.
little different. You might have another wing in quadrant 2, or you could have an upside down wing in quadrant 3. Depends. We don't care. We're looking at quadrant 1. In quadrant 1, which is the most important to us because 99% of the time we're sort of looking to the right, starting at the y-axis and going to the right, many, many times, especially in this class. And it says in quadrant 1, so the region
zero,
that's bounded
give
in
us
quadrant
everything.
1 is this region right in
Plug in
here. That's the
1.
region we're trying to find the area of.
Gives us that.
Okay, so you all find that area. Go ahead and figure out what that area is, and I'll come by and pick up those surveys that I handed out.
15.
While you figure that out. And notice you could use a dx, or if you wanted to be a contrarian, I know there's some of you in here, you could go dy in this
Questions?
case.
When you found
You could go dy.
in the green, like weren't we supposed to get
Give me a
everything to one
contrarian.
side and set it equal to 0, but did you just do it that way because
So-
it's like that?
So setting, when you have a nonlinear equation, everything to one side and factoring, that always works if the thing
Of
is
course,
factored.
if you use
The
dy
one
instead
example
of
where you don't
dx,
have to go all the way
Gonna get
is
the
if you
same
have
answer
just a
if you do it
single
right.
square term. In that case, they call it extracting roots. In that, if you can isolate the square term all by itself, then you don't actually have to go all the way. But of course it would work. If you have x squared equals 1, you can subtract it all the way to the left and back over. And you'll still get the same answer. So the good rule of thumb is everything to the left and factor. But if you have just a single variable term and it's a square, then you could do that. Question?
Thank you.
Area for the square, and then you said that answer and plugged it into the integral for the volume. How did you know that you're supposed to do that?
Because the integral of area gives volume.
So that power rule works for any power of
Is
x.
area, integral of area.
Well, except 1.
So the idea is that
That's
if
the
you
one power of
find
x it
area
doesn't
by
work for?
cross-sectional square. And if
X to the
integrate
negative
that,
1, because if you add 1 to the exponent, you
so
get
the
0.
area of
you
the
can't divide by
square gives us a function that we can then integrate to get the total volume. So the
So we'll
summation
start out
is
by
basically
using a
adding
vertical
up a
element
bunch
and
of
a random
square
X.
slices. That's what the integral is doing.
Question?
Wouldn't it be more easier for
Adding
to
up a
go,
bunch of square slices.
horizontal?
About the same.
Okay.
Yeah, it should. We'll do it both ways. We'll do it both. So my instinct to do it vertically is because the functions are presented
We
as
see
y
that our
values.
two curves
Right, they're presented as
are
y
symmetric
values,
around
which
the
means
y-axis.
vertical element.
So
If we
instead
want
of
to do a
going from
horizontal, of course we
-1 over
can,
to
but then we
1,
have that
we go
extra
0 to
work of
1.
solving both of them for x.
Or if we're
We'd
contrarians,
have
we
to
could go -1 to
change
0.
those. Okay, so we'll do it both ways, though. So we need this intersection point. So we're going to set the curves equal to each other
Okay,
to
another
find
one.
that intersection point.
So this one again is created
When we have
geometrically.
x raised to a power, we'll just undo the power by raising
We've got
both
the
sides to
solid
3/2
with a base in the xy plane.
because 2/3 times
y
3/2
equals
is 1.
cosine. That's a
So it's x
function
to
you
the
would not
1.
be expected to have to graph. Y equals
When we have a rational
That's not a
exponent,
common function. So
ideally
that would be
we
given
use
to
the denominator first. The denominator is
So
a
they
root.
say to look on the interval
Base
pi over 2
is a
pi over
perfect whatever that is.
Now they
then
tell
we
us
do
that
it.
cross
So that's a
sections
square root, and that's a
are
perfect
going to
square,
be
so we'll do that.
perpendicular to the x-axis, so we draw
it's
this
gonna be that
element
point of intersection
perpendicular
there.
to X.
So this tells us that the area
And those
will be
cross-sectional
the integral from 0
shapes
to 8.
Are going to be
Upper curve
isosceles
minus
right
lower
triangles,
curve.
where the horizontal leg in the xy plane
So that'll
and
be
the
our set.
vertical leg is upper
Above
minus
the
lower.
Upper curve is the
So
y value of
isosceles
4.
triangles,
Lower is the
legs
y
have to be-
value of x to the 2/3.
the two legs are equal. An isosceles triangle has
Antiderivatives
two legs
for both of these.
that are the same.
So we add 1
So
to this
this tells
exponent, so
us
we add
that
3 over
the
3, so
distance
that
right
makes it 5 over
here
3.
Is also
Divide by 5 over
Square
3,
root.
that's the same as multiplying by 3 over 5, 0 to 8.
so. What is the area?
Once again, plugging in
Our-
0,
Cosine X.
not going to give us anything. It's a
Let's see,
decoration.
so 1/2 the base times the height. So maybe what you
You don't
said
have to
was
worry about
right.
0.
1/2
Plugging in the 8
base
gives us 32 for the first term.
times the height.
For the second
That's what
term,
you said, right?
again, if we can use the denominator first, we will. The denominator is a root. In this case, it's a third root.
So that is
And
the
8 is a
area of
perfect
the
cube.
triangle,
So
cross-sectional
the
triangle at
cubed
X.
root of 8 is 2. 2 to the
And then if
5th
we integrate that
is
cross-sectional area,
32.
we get.
So we'll have 3/5 times
Volume.
32.
So our volume will be the integral.
I'm going to factor out a 32 here because it's
We know that
a little bit
the endpoints
less
are minus
multiplication.
pi over 2.
If we factor out
So
the
if we wanna
32,
do
we're left
symmetry,
with
we
1
would
minus
go
3/5. And that we can do in our head. That's 2/5.
Double it. Put a 2 in front. So this 2 is a symmetry.
So we end up with
2.
64 over 5.
Symmetry.
Yes.
0 to pi over 2. Is everyone okay with that?
It's coming back. It's coming back.
General goal.
Starting to feel good. Start to get that tingly, warm feeling. Yes.
Yeah. If you can, it's always going to be easier. if you have
So
a
much
formula.
better than writing an essay.
Definitely we can do that. So the 2's cancel.
In my opinion.
Derivative.
Not in my wife's opinion. She's an English teacher. Yeah, I know. Okay.
Cancel. Integral cosine of sine.
So let's go
Sine of
ahead
0,
and do this
Minus pi over 2.
the other way. Let's suppose that we wanted to use a horizontal element.
Sine of
We
pi
use a
over 2.
horizontal
Pi over 2 is the
element.
top of the circle. Sine is the y
We'll
value.
talk about this more generally in a
volume
moment.
of
But
one.
let's just, this is
One
a good
cubic
opportunity to just jump in and do it.
Nice.
So these
Volume.
functions have to be x values, not y values.
One.
Y values gives us vertical distance, horizontal distance is x values. So the x value on the
Rocking
left
and
here is
rolling.
x equals 0. The x value on the right is x equals y to the 2/3. Excuse me, y to the 3/2. Let's. So that's the x
So let's
value
think
on the
about
right.
the discs. The
X value on the
discs
left
are
is
a lot
x equals 0.
of, in a lot of ways,
So
much
our
easier.
area, which will
You know,
give
sometimes
us the
those
same
geometric
answer, is
cross-sections,
integral 0 to what?
although not extraordinarily,
0 to 4.
extraordinarily difficult,
Because
they're a
these
little harder to
horizontal
visualize.
elements are sliding
when you're just taking
with
a
respect to
region
the
and
y-axis.
rotating it
The
around an
horizontal
axis,
element for
a
all
little bit
these
more.
y values between 0 and 4.
So
And now,
when
horizontal
we have this
distance,
disk set up,
right,
the area of the
minus
disk is
left.
pi r squared.
The right x value
And
is what
the
of 3
function that
halves.
you're given is always
The
going to
left
represent the
x value is
radius
x equals 0.
if your region is
The
touching
thickness of our
the axis
rectangle is a
rotation.
dy
Because that
it's
function
lying on
is
its
telling you
side.
how far away you are from the axis of rotation, how far away the curve is from the axis of rotation. So if we look
If
at
that's
this
a y and
triangle
that's a
here,
dx,
and we draw a
sounds like
vertical
a
element,
great opportunity for
at
me
a
to use my
random
red
x.
pen.
and we rotate around the x-axis,
Wonderful.
we can kind of see all these disks. Right? This thing is going to
So then we add 1 to the exponent, so we got 2
2
over 2.
And the
Get
radius
5
of
over
that
2, divide
disk
by 5 over 2, that's the same as
is
multiplying by 2.
exactly whatever the function is at that x value.
Plug in the
radius
4.
is the function.
Square root of 4 is 2.
And
2
that's
to
what they're
5 is
showing in this
32.
formula. Pi r
32
squared.
times 2
R is
fifths.
just given by
Right
whatever
there.
the function is.
64 fifths.
So in this particular case, our volume will be pi times the radius squared. Well, the radius is given by the function.
All right, any questions
minus 2x.
thus
Well,
far?
that is our setup. And
No
they
questions?
give us our limits of integration.
Comments?
They tell us that that point is 1 and that point is 0. So
Why not?
How do we know the equation for y on the red line?
This one here?
Yeah,
everybody see
yeah.
So what was the question? How do we
So like horizontally, like placing it.
how do we go from here to here?
Yeah.
So if we have,
we
so we
are gonna
want to
have to
isolate
FOIL this
the
out.
x. So if we have that y is equal to x to the 2/3, then we are going to raise both sides of this to the 3/2, so that 2/3 times 3/2 is 1.
Once again,
So that'll
the
give us what?
antiderivative
That'll give us
for
the
all these
isolated x.
powers of x.
Yeah. So remember that when you have a power raised to a power, you multiply the two together. Power to power, you multiply. So if the powers multiply to 1, that's kind of our goal, because that takes away that exponent and leaves us in an exponent of 1.
I'm just a little confused with now like why you add both equations in at the top.
Plugging in 1, we just get the coefficients.
Here,
Yeah.
what, and say that, restate what you said?
I'm just confused on like why you put in both of those equations right there.
Gotcha. So this right here represents the height of our rectangle. This represents the width or the thickness of our rectangle. So it's base
And
times
now
height.
we only deal with
And
units if they
this
give us
black
units,
line
and none
is
of these
vertical.
problems have any units.
And whenever you find a vertical distance,
So we'll get
you
to
do the
some-
upper y,
do you like
subtract
units?
off the lower y.
From physics.
So if you think about a
So when we
very
get to
simple
6,
example,
7,
if you
it's
just
all
have your
about
axis
start
right
the
here,
application section.
and if
So
this
then
is
we-
up here at 4, and this is down here at
most of these.
-2, what's the distance between the two? 6. It's the upper one minus the lower one. So whenever we want this vertical distance here, it's always upper minus lower. So we're doing the same thing. It's just that our upper and lower are functions now
And
instead
we'll get into
of
con 7 where we're trying to
But it's the
find
same
the
concept.
work done,
upper minus
in
lower.
a tank or something.
And when we go horizontal, right minus left.
Because the units tell us everything.
Is the general takeaway that any
Here the units are boring. It's
is
just
solved
cubic meters or
doing integrals with respect to x?
Yeah, when we get to 6, 7, we'll use we'll do a lot of units. What time does this class end?
We would have to
15,
set up
okay.
a separate. We should go early.
And the top little
Yeah, no, I
jump.
think it's
Oh, yeah,
fine.
If I drew it properly. So you could theoretically set it up.
This is a
But
dictatorship.
if you were to draw this horizontal element here, so this is still in the same curve. So it's
All right, we'll do,
still the cosine
oh, an
function,
exponential.
but it's a translated
Yes.
cosine value. So
Exponentials.
it would be very hard.
Exponentials and logs.
Technically,
I have to
theoretically,
fill
you
in
could
all
do
the
it either
leaks
way
in your
with any
boats.
situation. You'd have to find all these
Okay.
intersection points.
So we've got this
90% of the time,
exponential
one way
decay
is going to be much
function,
easier than the other.
and that's going to be our upper
Now,
boundary.
if
That's
you
gonna
don't
give us
have
our-
anything weird,
our
like this
radius.
is both
We draw
simple for a
vertical
horizontal element
and
and simple for a
the
vertical. So in
radius
this case,
of the
it's gonna be
corresponding disk.
difficult. Remember, the region is nice in both
Yeah,
ways.
it's a little messy.
I just want to confirm.
Yeah.
So when you say upper,
So the
you
disk that
mean
we're going to create has
the
a radius
values
of r.
in this case for y equals 4 are higher
Yeah.
up until that point than for x to the 2/3?
Yes.
Okay.
So
Yeah, so
tell
the
me
upper
what
literally
the
means it's
area of our
above.
disk is then.
You know, so this is going to be the upper curve. This is going to be the lower curve. So it means whatever one is has a higher value.
So how does that simplify?
So for when you use the y's,
Everybody agree with that?
why don't you subtract like the
Power
y
to
equals 4?
power multiply.
So when we're doing horizontal,
multiply.
it's x minus x. What is the x value on the left?
Power to power multiply.
Zero.
So that is the area of our disk.
Right. This curve
So
right
the part that
here
gets a little
is the
funky
left
now is
curve.
that the volume
This curve is no
zero
longer part of the
from
scenario
0
anymore.
to
That
natural
comes into
4.
play with the limit of integration.
I
But the
e to
curve on the
negative
left,
x
the boundary curve, is the function x equals 0. It's the y-axis.
Close.
So the x value here is y to the 3 halves.
So we
The x
talked about
value
this at the
here
very
is x
end of our
equals 0.
class on Wednesday
Right,
through
so this
Zoom.
curve up here, no longer, the
Zoom
blue
is
curve is
Zoom.
no longer part of the functions that are being
When
subtracted.
the
It's part of the boundary.
substitution,
It's
I
part
don't
of
know.
the limit of integration.
Someone was asking about this at the end of the class.
You could
When we
rotate
have
it
a
and
linear
change the variable.
substitution, we can use a
It'd make it a
technique
little more
called
complicated, but
reverse chain rules.
You do like.
In Calc 1, you would have done this with U substitution.
Why would you want to?
But what we noticed
So
in
if we had
exponent
something
is
that was-
this is
Like
linear.
if it was a bunch of curves.
So if we had
linear
some sort
because
of
the power on
like
the x is
polygonal
1.
path around
So
the
if you
outside of
have
it,
a substitution that's
You
going
could.
to be linear.
but
So it's
the
gonna
problem
be like
the
mx
problem
plus
is, you know, what we were
c.
sort of just alluding to, you'd
Then
have
you
to
can
subdivide it into a
avoid
bunch of
doing
little
U sub.
regions. We are going to have a way,
Substitution
once
every
we
single
learn
time.
in Calc
Your
3,
substitution is linear.
you'll have a way to
You
find the
do it.
area in a region that has a polygonal path along the outside by doing something called the line integral.
Yes, x is
which
raised to the
integrates
first
along curves, even though it's
So
called
it's
a line
linear if
integral.
it's in that form, 5x plus.
So yeah, but you
something
could,
like that.
absolutely.
Raised
You
to the
definitely
first
can.
power.
So
what
here
we
is
can
the
do in this
formal
case
method for integrating with respect to
we can
y instead of with
factor out
respect
the
to
pi
x.
first.
So notice
And then
all
the
of these
integral or
setups
the
here
derivative
are
of an
set up for a
exponential
horizontal element.
starts
All three of these, red on the left, black on the right, all three of them are set that way. And if you tried to draw a vertical element, you wouldn't have the scenario like we just had in the last slide, where you have a common upper and a common lower. You can imagine drawing your vertical elements in here and having all sorts of different scenarios.
reverse chain rule.
Right, the only way a vertical element works is if
RCR.
you can have, no matter where you draw it, there's the
And
same
that
upper and
works
same
when
lower.
The substitution.
So here, no matter where we draw our horizontal, red, left, black, right.
No.
Red, left, black, right, no matter where you draw the horizontal element. But if you draw a vertical one here,
So
you know,
then
you could draw it
just
in
have
different
to deal with
places
our
and have
substitution
different
of the
curves
limits
that are
now.
on the top and on the bottom. So you don't want to use
Let's
vertical
pull the
elements.
negative pi over 2 kind of out to the front, and we'll think of just evaluating the limits in this, because constants can always factor to the front. we're gonna
So
bring our
in all three of
limits
these
of integration
cases, though, the
just into
vertical,
that
the
yellow.
horizontal elements are going from C
So
to
this
D.
is e to the minus 2 ln of 4.
Does that make sense?
Yeah.
So it doesn't
Minus
matter if the
one.
curves are pinched down at a single point at D, or if there's actually a space there. You're drawing your rectangles, your sleeping
In
rectangles,
this
they're all on their
case, the 0
sides.
matters. We
All
have
the way
a lot
up
of
to D.
integration where the 0 didn't contribute.
It's just here,
It matters.
the horizontal rectangle
So
here is going
then
to
we
be,
get
it's going
minus
to
pi
pinch
over
down to a
2.
point.
And
So
this
one
is
half
going to
won't be
be
as-
1/16 minus 2.
It will be a degenerate rectangle. Those degenerate rectangles, beware of degenerate rectangles.
Right?
They're always trying to lure you in.
So remember that
Okay, so
coefficients to a log.
our basic setup, same scenario. Same scenario. This is representing the height. It's just on its side. It's still the height of the rectangle. It's just that the
Move
rectangle
into the
sideways. And this
inside
is
of
still the
log
base or the
become
width of the
exponent.
rectangle.
And then 4 to the negative 2.
So let's take a look at this example.
1 over 4 squared. which
So I'm going to
is
draw a vertical, a horizontal element.
So the
So this
coefficient
is a
comes up
horizontal
as an
element at a
exponent,
random y.
And then the E and the ln are going to cancel.
When we get to
E and
finding
ln are
volume, it's going to be
inverse
helpful to
functions
put
of each other,
this
so
sort
they
of
cancel each other out.
location of your
We're just
representative
left
element.
whatever is
You don't really
inside
need
the
it yet,
log.
but it's
So
helpful to
that's gonna be
think
16.
in this way.
Okay, so then this all becomes.
Now this function on the left, the red function, is a piecewise defined
That's going to
function.
become 15, 16. So
That
the negatives
piecewise
and negatives
defined
cancel, so
function
15 pi.
is defined differently for different pieces of the domain. So what about this red curve here? This one has equation x equals y,
Okay.
whereas what is the equation? of this
So let's see, are we at the shells yet?
one? Yeah, that's going to be x equals negative y. So a piecewise defined function, you're going to have
So
to
let's
break it
go
apart
over-
and
Roberto
find
asked
the
this question
different
earlier.
pieces.
And I put it
based
up
on
here
function.
in this question space. Let's
So
talk about this for a moment.
another thing we can use here is symmetry.
Maybe I won't
We
write it all
definitely
down.
see
It's
that
part of the homework
both
once
these
you think about
functions
it,
are
but-
symmetric about the x-axis.
So here
So
we're given
let's go ahead and find
a
the
drag racer
area
that accelerates at 64
of that top
That's the
region and
acceleration.
double it.
That's going to be, and we're going to assume that it's a drag racer. Initial velocity
Alright,
is
so
0,
our
initial
area
position is 0. Starting at the
Is
at
going
the
to
start
be,
line.
we're going to put in a 2 for that symmetry.
So it says
this is a
determine
symmetry
the
2.
position function
We'll say that that's by
for
symmetry.
t greater than or equal to 0.
All right,
So starting
so
with
let's see.
acceleration
Limits
is
of
constant.
integration, we haven't found those yet.
And this
We're gonna
funny
go-
drag
the
racer
lower one
is
we know
take
is
off
0.
64 feet per second squared, and what's his velocity?
So we're doing right curve minus x curve, left, right minus left. So this is the x value on the
So we're
right.
gonna integrate, if we
2
do
minus y
t, it'll be
squared.
64t
The
plus
x
c
value
equals
on the
sum
left
of
is
v.
x equals y. So
0
you
because the
right
initial position,
minus
initial velocity is
left.
0. So 64t
So the right x
would be the velocity
minus
times
the
t.
left x.
And then if we want to get to position, what are we going to do?
Antiderivative.
Antiderivative again.
Now let's deal with our limits of integration. So we're going to set our two curves
Plus
equal
c,
to
but
each
that's gonna
other.
also be
So
0
we're going to
because
set
position is
y
0.
equal to 2
All
minus
right,
y
and so
squared.
that'll
So
get us through
setting
these
these
first
two
questions. First
curves
two
equal
parts.
to each other.
And then this one says at this rate, how long will it
Everything
take
to one
travel
side and
1/4
factor.
mile?
Same as it ever was.
So we know that displacement and distance are going to be the same, right? The car is not going to go back.
So this gives us y equals 1 or
So
y
if we
equals
do the
negative 2.
integral, we want the integral to equal the
Which of
distance
those y
traveled, and the
values is the y
displacement
value
integral
we're looking
should
for?
equal a quarter.
1.
So then we're going to have to
So we're gonna go
integrate,
from
and we're
0
going to
to
have a
1.
letter in the limit of integration.
What is the negative
and that's
2
going to be a
giving us?
variable, so then we have to sort of back substitute to figure out what the t is.
This one
We
right
know
here.
that the integral has to equal
No. We just
a quarter.
talked
So
a
you have
moment ago
something
about the
like
fact
this,
that these are
1/4
symmetric.
Equals integral
So
from
that
0
y
to
value is
t,
plus 1. That one should
something
be
like
negative 1. So what does the minus 2 mean then?
something like that, right? That's going to end up being a function of t on the right, and then you would solve that for t. So think about that. We can talk more about it.
This curve right here, x equals y, it does
All
not
right, let's,
stop at the origin.
Wait, you had a question? What
Right?
was that
X
question?
equals y continues on, doesn't it? Doesn't that continue
all right.
on this way?
We'll go with that. If
Then
you
this
get in
curve
there and you're still not
continues
sure,
on.
just post it
So
in
that
there and
negative 2
and I'll
is going to
reflect
correspond
it.
to the intersection if you consider this curve in its entirety. We
There
kind of chopped it off because it's part of an absolute value function and are just focusing up here, but that curve in and of itself, it goes on forever, down into quadrant 3. So that negative 2 is where x equals y would meet that graph down in quadrant 3. All right, so let's go ahead and finish this off. So we have an antiderivative, very easy to find for all three of these terms here. Plugging in the 0 doesn't contribute, so we just have to worry about this.
All right, good to see you in person. In person.
Distributing the 2 actually seems like it might help.
Absolutely.
Definitely
Oh, totally fine. It's the first day. I know.
And 4 minus 1 is 3.
No,
Subtract off 2/3.
You're totally
Make
fine.
that.
Obviously,
by 3 over 3.
Another example of integrating horizontally with a horizontal element. So we will once again draw our horizontal element wherever we so please.
All right, so and we see that the curve on the right is what color? Red. Any questions? The curve on the right is the black curve. So we're going to do right minus left. So we have to do the red curve minus the black curve. So it's going to be this one minus
So if
that
we've
one.
done this
So the area
by symmetry would the
will
area
be
be
right
zero?
curve.
So do we get different answers?
No, the area will not be zero
Minus
here.
the other curve.
If we did it vertically,
We'll put it in parentheses.
we would be doing this vertical element, so we do this red on top and y
that's
equals
our
0
basic
here,
setup.
and over here we
Right
would do
minus
the black on top and the
And now we
0 down
need to
there.
know the limits of
We
integration.
add those together
so we've
and then
got to set
multiply
the
by
curves
2
equal
for
to each
symmetry.
other, because we need to know what the y coordinates are at those 2 points.
The x-axis.
These horizontal rectangles.
Now,
are
so the
those
question here says
y-values.
find the area.
Oh, not net area.
Yeah,
We'll
not net
set
area.
it equal and find
Yeah,
out.
net area would be 0. Yeah, so it's asking us to come up with a
Set them
scheme
equal
to
to each
find
other.
that area.
Okay.
Yeah, it's not saying
And
just
solve for
integrate
y.
and figure out the net area.
Okay, I see.
Once again.
All right, let's go ahead and take a 10-minute
nonlinear
break.
equation, everything.
Oh, you have a question.
Yes, I did.
Oh,
So that little bit in red there,
here?
yeah, is that setting the two equal to each other to find where they intersect?
Correct. Yeah. So we're taking this x value and this x value, and we're setting them together to figure out where they have a common y.
Okay, and so when there's a -2, that's because that's looping back around and crossing with it again below?
Right.
All right.
Yep, that's
And
right.
then I was wondering,
Not usually.
there at the very top, how do you know which to subtract?
Right minus left.
Okay.
We can make up some.
So
more
this
complicated
curve, so if we look at our, always focus on your element. So if you look at your horizontal element there, the curve on the right is
Okay,
this
so
one over
setting
here,
the
which
curves
is
equal to
2
each
minus
other,
y squared.
Everything to one side.
And if you go to the
factoring
left
zero
of your
product
element,
rule,
that's the one that's on
-3
the
and 2.
left, which is the
Those
x equals
are
y.
the y
So how do you
values
determine
that will
which
act
one
like our
is
limits of
right
integration.
and which one is left if you don't
-3 to
have
2.
a graph in front of you?
That's why we always draw the graph.
So the
Okay.
lower.
So we just
limit,
have to draw the
Yeah, you want to draw the graph because it's not necessarily obvious. Now there is a way,
Any issues?
by deductive reasoning, if you know you're finding area and you come up with a negative answer, you probably subtracted them wrong. Because the area is
Then we're
always
going to distribute the
When
minus
you say
sign
right minus
and
left,
collect
is it
terms.
like the
So we're going to have
furthest
minus
left point or
3y
the
squared.
furthest right point? Like,
So when you look at your blue element there, this curve right here, you can
Minus
kind of
3y.
ignore the extremities of the curve. Just
right, you're
focus
just
right
looking
here.
at the part that's being surrounded. And
Yeah,
Okay.
looking at that point right there, the element is surrounded right there. That's the
Power
curve on
rules
the
all
right.
need to integrate here.
This red one is the
Nothing more
curve on the
complicated
left.
than the power
What do you
rule.
do when it's more obscure?
It won't.
It won't be.
Never.
Okay.
Never. Never. Let's take a 10-minute break. And then we'll look. If we come across an obscure one, you can tell me. And then we'll analyze it.
Okay.
Yeah, there will be some that are a little bit more obscure for sure.
Now we have to do some arithmetic.
Plugging in the 2 is going to give us -8. 2 there is 4. 4 divided by 2 is 2, so that's -6 plus 36. And then we're going to subtract off
Plus 27?
the the antiderivative at -3. So we're going to plug in -3 here. So it's going to be 81. Plug in the -3 here. We're going to get 9, which is 27 over 2 with a negative. Plug in the -3 here. We get -54. That look okay to everyone?
That looks disgusting.
Yeah. We've definitely seen better. Some math is nicer to look at than other math. Okay, so let's do some subtraction here. So 22, and then let's combine these two. What's that, 27? And that's going to have a minus in front of it. And then plus 27 over 2. So then we get -5, get a common denominator of 2, so -10 over 2.
Why is it 81 not 27?
Let's find out. Right here?
Yeah.
So plugging in 3, I don't know. Great question. When we plug in -3 right here, it becomes positive, but it's only 3 cubed, so it's 27. Thank you. Much better. And then 27 minus 54 is -27, but that minus will make that a positive. That look better?
Yes.
Thank you.
Oh, interesting.
Thank you for catching that. All right, so then what's that? 49 plus 27 over 2, common denominator of 2. So 98, 99, 125. 125 halves. Concur?
Yes.
Thank you.
I thought I was bad at that.
Bad arithmetic. The calc part seems so much easier. Fractions. All right, questions on any step? All right. Here is a region that could be integrated either direction. You could use a horizontal or a vertical. Now, when we look at it, both functions are presented as y values. So it makes more sense to just go ahead and go with the vertical element, since that's how it was presented to us, and we don't have to do the extra work at converting. But you could use either. Either will work fine. So let's go ahead and say that the area is equal to the integral of upper minus lower. So the upper curve is the red one. The lower curve is the black one. And our limits of integration are 0 and 1, which you can kind of see by inspection. If you don't see it by inspection, you set them equal to each other and solve. So, square root equation. What do you do to both sides when you have a square root equation?
Apply the square root property.
So we'll square both sides. Yeah. If we square both sides, we end up with this. And then
C is equal to 1.
everything to one side and factor. Nonlinear equation. Everything to one side and factor. Never, don't divide. You cannot divide by a variable. Variables can be 0. So we see that the two places of intersection are at x equals 0 and x equals 1. So that tells us that our limits of integration are going to be 0 to 1. The interval upon which this region lives is 0 to 1. And we can integrate each term easily with the power rule. So this is x to the half, so that becomes x to the 3 halves multiplied by 2/3. And that becomes x to the 4th over 4. So we end up with 2/3 minus a 4th. Common denominator of 12. That's going to be 8 minus 3. That'll be our result. Any issues? You look like you have an issue.
No, I'm just looking.
Okay. I'm going to wait until I see a change in expression. Any questions? You have a question?
No.
That's all right.
I have a homework question whenever we have those.
You have a homework question? What homework question?
Number 4.
Number 4 and 6-1?
Yeah.
All right. We will get to it. Okay, so we've got to find the area here of the region described by these two curves. The first one is easily graphed, sine of x. You know, sine of x we know has the 3 key points there, key point there, key point there. So there's sine. Yeah.
And when we start doing the homework for this one, is it okay if we use Desmos?
For any graph that's not a basic graph, for sure. Like there's one graph that was like something like 1 over the square root of 4 minus x squared or something, which you wouldn't be expected to know that graph. You should be able to graph like sine, these things you should graph. Okay, what kind of curve is that second one?
Half circle. Oh, the second one.
That is a, you can say it. Parabola, right? It's an x squared, so it's going to be a parabola. And we know that parabola, and is it going to open up or down? It's going to open up because it's a positive x squared. So we know it's a parabola opening up. And now we don't have to get super precise with it, but when we look at it in this factored form, we see that the zeros are 0 and pi. And we know that it opens up, so we know the vertex is in the middle of those two. So we don't really care how far down it goes. We could find out if we wanted to, but we don't have to. This is going to be y equals x squared minus pi x. So we just want to draw the graph close enough that we know what's on top, what's down below, what's above, what's below.
Well, parabolas are symmetrical. Don't we just split the difference?
Yep. The vertex is going to be right there at pi over 2.
Okay.
But we don't have to plug in pi over 2 and figure out what the exact y value is.
Okay, I see.
We don't have to do that. So this tells us then, if we draw a vertical element, that our area will be the integral from 0 to pi. So they're telling us that we're going to go 0 to pi. And then the curve on top is sine of x. And the curve down below is that one, so we're going to subtract off that one. So that will be our setup. Good? And we can go ahead and distribute the minus and integrate at the same time. So integral of sine is minus cosine, and then minus x cubed divided by 3, and then plus pi x to the 2 over 2, 0 to pi. First, we'll plug in the upper limit, plug in the pi value. So cosine pi is -1, multiplied by a negative. That gives us 1 minus pi cubed over 3 plus pi cubed over 2. Minus antiderivative at 0. This part of the antiderivative at 0 is 0. So we have minus minus, which is plus cosine of 0. Cosine of 0 is 1.
Wait, how did you get the integration limits in this one?
The limits of integration are given to us.
Oh, okay.
So they tell us that we're going to go between 0 and pi.
Yeah, they do.
Math is a visual activity. So then we're going to end up with 2. And if we get a common denominator of 6 for these two terms here, we're going to have minus 2 pi cubed and plus 3 pi cubed, which is 1 pi cubed over 6. So there's our answer.
Can math just be renamed to I Spy?
No. I refuse to rename math to I Spy.
I Spy with numbers?
I Spy with numbers. There we go. Man, isn't it getting a little boring being in 2 dimensions?
No.
Not at all.
Right?
Very
It's like,
In fact, I think it's too many dimensions.
I feel like it's time to go to 3 dimensions.
It's like we live in 3 dimensions.
No.
It just
You live.
It feels. How many dimensions do you live in? Never mind.
I can't even jump that high.
Okay, so now we are going to extend the ideas of integration to find volumes. And so our strategy is very similar. We're going to use Riemann sums, at least in the background. And the idea is that we are going to have a solid object which could be created in a couple of different ways. We'll talk about that. When we just have a solid object, we can take a cross section. So a cross section is going to be, there's going to be no width. It's going to be infinitesimally thin. It's not going to be a little volume. It's just going to be, a cross section is 2-dimensional. It's a region. But then, just like with the element, when we drew a vertical element, it had height, and then we sort of puffed it up to have thickness, which was dx. Same idea here. If we take our cross section and then we add a little thickness, then we're going to call it a slice. So a cross section is 2-dimensional, and a slice is 3-dimensional, but very thin. So we're going to call this slice, we're going to say that it has cross-sectional area, whatever the area is over here, and then the thickness is dx. And you can see that if you subdivide your region into a bunch of those little slices, it's going to approximate the volume. So the volume of that slice is the cross-sectional area times the thickness. So this in here is the volume of a slice. And then we add them up, and we get an approximation. And then we do what you learned in Calc 1. You take the limit of the Riemann sum. And so as you let n go to infinity, your approximations get better and better and better and better. And then when you take the limit of your Riemann sum becomes a definite integral. And we know how to deal with definite integrals. Definite integrals are very manageable. So that is the integral that we are going to use for volume. All we have to do is integrate cross-sectional area. So there are 2 ways to think about this integral. You can think about it conceptually that the integral of area gives volume. You can think of it kind of that way. Just like what we just did on the previous slides, we integrated length to get area. Right? Our functions were measuring the length from the x-axis up to the curve. If you integrate length, you will get area. If you integrate area, you will get volume. So it kind of parallels the acceleration, velocity, position argument, where you have 2 derivatives and 2 integrals that line up to go from one direction to the other. So what is the area of a circle? What is the derivative of this with respect to r? Voila! Take the area of a circle, you take its derivative, you get the perimeter, you get the distance around. You take the derivative of area and you get distance. What? So, same thing holds for volume and surface area. Most of us don't know the surface area of a sphere, but many of us probably remember the volume of a sphere. Volume of sphere, 4/3 pi r cubed. Never seen that before. How many dimensions do you live in?
Not enough, apparently.
So what is the derivative of that with respect to r?
Same.
So differentiating that with respect to r gives you the surface area of a sphere. So that connection where you integrate length to get area, integrate area to get volume, we're going to see that a lot. You can also think of this less conceptually, and you can think of it more mechanically, in that this is a slice and the integral is just summing up all the slices to get the total volume. A slice is a mini volume, and the integral is just summing them up to get the total volume. So you can think of it either way, conceptually or more mechanically. So here we go. We've got this solid object, and this solid object is created geometrically. They say start with the curve y equals the square root of 3 minus x, which is that curve right there,
and look at the interval 0 to 2. So here is a region in the xy plane. That is the base of the solid. So it's in the xy plane, and the solid is sitting on top of that. So the xy plane region is the base of the solid, and then the solid sits right on it, right? So what they're going to do is tell us how to create the solid. First thing is that when we talk about cross sections, they are always perpendicular to the base of the solid. We're not dealing with any sort of weird angles coming into the base of the solid. So we're not dealing with any sort of weird tilted prism type things. Base, cross section. And the cross sections, what we are going to figure out, are the cross sections parallel to the x-axis, or are they perpendicular to the x-axis? Those are our two choices. Parallel to x, perpendicular to x. Which, the other side of the coin, you could say parallel to y, perpendicular to y. It doesn't matter. It's one or the other. It's going to be with respect to one of the axes. But the cross sections are always going to sit upright, perpendicular to the base. So this says the cross sections are perpendicular to the x-axis, and they are squares. So this is why I drew this element here vertically, because it says perpendicular to the x-axis. So that element is perpendicular to the x-axis. And then we imagine these squares are coming straight out of the board. So whatever this distance is right here, that distance is going to then tell us how far out of the board we're coming, because we're building a square. Question?
So is it going to be the case that it's either parallel or perpendicular,
yes,
depending on the problem?
Yeah, exactly. So it's one or the other. Yeah. So if they would have said that we were going to draw cross sections that were parallel to the x-axis, we would draw our element that way. So what's the area of a square?
Base times height.
Base times height. And even more simply, since base is equal to height, it's the base of the square squared. So the area of our square is, there's the base of the square. Using the word base, we have to be careful. There's the base of the solid, and then there's the base of the square. We could call this one side of the square. And then the height of the square, same thing. So that is the area of the square at x. So if you plug in x equals 2, you will get that this square that's coming out of the board right here has an area of 1. 3 minus 2 is 1. Or you could plug the 2 in here and say that, oh, the base of the square has length 1. That means the height of the square is also 1, so the area must be 1. If you look here at 0, the area of the square is going to be 3. What are the dimensions for the square at 0? What are the dimensions of that square at 0? What's the height and what's the base? Say again?
3.
No.
Root 3.
If the base, if the dimensions were 3, it would be 3 times 3, which would give an area of 9.
So root 3.
Root 3 and root 3. So if we look here at our curve, the curve here, if we plug in 0, we'll get that this y value is root 3 right there. That's root 3, which means then we come out of the board root 3 also. So that square will have sides root 3 and root 3. Okay, so now to get to the volume, all we do is integrate area. So volume is the integral of area. And they tell us that we are looking on the interval 0 to 2. So they tell us the domain here, 0 to 2. So upper limit 2, lower limit 0. Yeah?
Determining the limits of integration, is it always like left to right, or is it bigger to lower?
So this element right here is perpendicular to the x interval, so that means we're using x's. It's a dx, right? The thickness of that is dx, which tells you your limits are coming from x. So then it's always left to right
Okay.
when it's x's, left to right. And then that's a pretty easy integral. So that'll be our volume. Hmm. 3D's not that bad.
Not yet.
So optimistic. The eternal optimist, Ryan Jones.
Pessimist, actually.
All right. We're going to try to change that this semester.
I wasn't ready the last bit.
So with this next one, the way the solid is going to be created is by, oh, hold on, maybe I'm misspeaking. I got distracted. So one other way that we're going to create solids, we can do it geometrically. We can say here's the base and all the cross sections are going to be squares or rectangles or triangles or semicircles or something. We can also do a rotation. So this one is, okay, so this is a rotation. So here we've got a region and we're going to rotate it around the x-axis and it's going to create cross sections that are disks. If your region is touching the axis of rotation, and we take this vertical element here, if it rotates around the x-axis, it's going to create a disk. And that's an easy geometric shape to find the area of. So this is a nice special case where we have cross sections that are disks. So this tells us that our curve that we're rotating is root x. That's going to act like the radius of this disk over here. And what is the area of a disk? Pi r squared. The radius is root cosine. And then we square it. So voila. That formula right there, that function is going to give us the area of the disk at x. So when we look at this solid object here, we can imagine all these disks that are stacked next to each other. The disk here at the end should have an area of what? 0. Let's check. If we plug in pi over 2, cosine of pi over 2 is 0. So yeah, that works, right? The biggest disk is going to be the one right here on the left, where the radius is 1. The area of a disk of radius 1 is pi times 1 squared, which is pi. So let's check. If we plug in 0 into our area formula, we should get pi. And sure enough, we do, because cosine of 0 is 1. So that is our area formula for the disk at x. Now, if we want to find the volume of this solid object, we will integrate from 0 to pi over 2. The cross-sectional area function. The antiderivative for cosine is sine from 0 to pi over 2. And once again, the lower limit's not going to do much. Sine of 0 is 0, so we can ignore it. And sine of pi over 2 is 1. So that is our volume. That is the volume of that solid object created by rotation.
Can you go again on how we got the radius?
So the radius is the function.
Oh, okay. Never
So the radius, does that make sense?
mind. It just doesn't look like it's like pointing towards the radius, so I thought the function was like of the curve or something.
So this function right here is measuring the distance from the x-axis up to the curve. And then that element right there, when it rotates around the x-axis, it's like a spoke. And it's going to create a disk. And so the radius, by definition, is going to be the value of that function. Right? Because that function is telling us how far away we are from the axis of rotation. So that's what the radius means.
Will we be expected to draw these like three-dimensional graphs?
No,
Okay, that's good news.
not if you want to pass. No, you won't have to graph anything crazy. Yeah. No. I mean, so drawing some of these things in 3D takes a lot of practice. So.
Yeah.
It's all about the shadow.
It's all about the shadows. In Calc 3, you will learn how to graph things in 3D where they will require you to graph them. Okay, so let's take a look at this one. So this is going to be described geometrically. So this one is not going to be a solid that's generated by rotation. This one, again, is defined geometrically. So what they do is they tell us the base of the region, and then they tell us what the cross-sectional geometry is going to look like. So here they say we've got two parabolas, and then we're going to create this element between the two parabolas. That's going to form one side of a square. And so then the height of the square must match whatever that distance is. And this little GeoGebra app thing here, you can, sometimes it's really helpful to see what the solid looks like, even if you can't draw it. But you can, a lot of these 3D graphers these days are pretty good. So this one, let's see if we can, so this one is editable. So what was it? It was, the upper was 2 minus x squared. 2 minus x squared. And the lower, was it just x squared? Yeah. So that's what this thing looks like. Should be able to blow that up a little bit. And you can see the little cross sections that are squares. You can slide this slider right here, and you can see the squares coming through. So that's what the solid's going to look like. And if you come down here to the opacity, you can sort of turn it into a wire frame if you want, and just sort of make it transparent. And you can put whatever two functions you want in there. Why is that not sliding? Whatever. Most of it's transparent. Yeah, so you can sort of see the squares as you move through, and it's going to create that object with those two sharp parabolas opening down. So it's not always obvious when they tell you the geometric cross-section. It's not always obvious what it's going to look like. Like, it's not totally obvious that it's going to have this nice smooth curve across the top. Like, it feels like maybe it should be not smooth. But trying to use a grapher to get a sense of what it looks like is helpful. All right, let's try to figure out the volume here. So, what is the area of our square? What is one side length?
X.
There is an x in it.
X squared.
So what is the upper curve here? So if you look at this, so think about if we go to this thing down here and we rotate it so that we're looking, let's see, that is x. So we're looking, it should be this way though, right there. So the upper curve is this one, the parabola opening down, and the lower curve is the red one that's opening up. So it's going to be upper minus lower. So the upper one is 2 minus x squared. And then we subtract off the lower one, so we get 2 minus 2x squared. That's going to be the length of that element, which is going to act as one side of a square. So 2 minus 2x squared. But then we square it. So the area of a square, base times height, both base and height are 2 minus 2x squared. And then we FOIL this out. FOIL. So that gives us the area of our square as a function of x. So as we slide through that x interval, the square that sits above it has that area. Yeah?
Where does the second 2 come in? Because it's 2 minus 2x squared?
So the upper curve is, so one length or one side of the square, I don't know what, I'm going to call it L for length of the side of the square. Let's call that L. So it's going to be 2 minus x squared. That's this upper curve. And then we have to subtract off the lower curve, which is x squared. Does that make sense?
Yeah.
So that'll be one side of the square. Alex?
Where does the square come from?
because we're finding the area of the square. So it's going to be that times that.
Oh, I see, I see.
And then we just integrate that function and we get the volume. So volume will be the integral of this, and then we just have to find our limits of integration. And how do we find the limits of integration? We're going to set the two curves equal to each other. So we have x squared is the lower curve, the upper curve is 2 minus x squared. So we end up with 2x squared equals 2. Divide out the 2. We get x squared is equal to 1, so x is plus or minus 1. So minus 1 to 1. Or you could go 0 to 1 and double it. You could use symmetry. Should we use symmetry? Having a limit of integration that's 0 is always nice. It's a lot easier to plug in 0. So we could do that. But we can only do that because both these curves are symmetric about the y-axis. Y equals x squared, symmetric about the y-axis. Y equals 2 minus x squared, also symmetric.
What problem was this again?
Say again?
Okay, I need that.
So let's integrate. Plugging in 0 doesn't give us anything. Plugging in 1 gives us that. Common denominator of, oh, let's do it all at once. 15, so that's 60, minus 40, plus 12. Questions?
When you found in the green, like weren't we supposed to get everything to one side and set it equal to 0? But did you just do it that way because it's simple like that?
So setting, when you have a nonlinear equation, everything to one side and factoring, that always works if the thing is factorable. The one example where you don't have to go all the way is if you have just a single square term. In that case, they call it extracting roots. In that, if you can isolate the square term all by itself, then you don't actually have to go all the way. But of course it would work. If you have x squared equals 1, you can subtract it all the way to the left and factor, right? And you'll still get the same answer. So the good rule of thumb is everything to the left and factor. But if you have just a single variable term and it's a square, then you could do that. Question?
You found the area for the square, and then you took that answer and plugged it into the integral for the volume. How did you know that you're supposed to do that?
Because the integral of area gives volume.
It's like acceleration and velocity.
Oh, okay.
So integral of length gives area, integral of area will give volume. So the idea is that if we can find the area of that cross-sectional square, and if we integrate that, then we'll get the volume of the whole solid.
Okay.
So the area of the square gives us a function that we can then integrate to get the total volume. So the summation is basically adding up a bunch of square slices. That's what the integral is doing. Adding up a bunch of square slices.
How did you get the green 2 that's in front of the integral? Where did that come from? Yep.
Because we see that our two curves are symmetric around the y-axis, So instead of going from -1 over to 1, we could go 0 to 1 and double it. Or if we're contrarians, we could go -1 to 0 and double it. What? Why would anyone do that? Okay, another one. So this one again is created geometrically. So we've got the solid with a base in the xy plane, y equals root cosine. That's a function you would not be expected to have to graph. Y equals the square root of cosine. That's not a common function. So that would be given to you. So they say to look on the interval minus pi over 2 to pi over 2. Now they tell us that the cross sections are going to be perpendicular to the x-axis, so we draw this element perpendicular to x. And those cross-sectional shapes are going to be isosceles right triangles, where the horizontal leg in the xy plane and a vertical leg is above the x-axis. So isosceles triangles, two legs have to be equal. The two legs are equal. An isosceles triangle has two legs that are the same. So this tells us that the distance right here is also square root of cosine. So what is the area of our triangle?
Cosine x divided by 2. Or
Let's see. So 1/2 the base times the height. So maybe what you said was right. 1/2 the base times the height. And I think that's what you said, right?
yeah.
So cosine x over 2. So that is the area of the triangle, cross-sectional triangle at x. And then if we integrate that cross-sectional area, we get volume. So our volume will be the integral. Now, we know that the endpoints are minus pi over 2 to pi over 2. So if we wanted to use symmetry, we would go
Pi over 2 to 0.
0 to pi over 2 and
Square.
double it. Put a 2 in front. So this 2 is a symmetry 2. Symmetry 0 to pi over 2. Is everyone okay with that?
So is the general goal to try and use symmetry to make that bottom limit of integration 0, and then it's just much easier?
Yeah,
to
if you
find
can,
out?
it's always going to be easier if you have a lower limit of 0.
Okay.
Yeah, definitely, if you can do that. So the 2's cancel, antiderivative of cosine is sine. The 2's cancel, integral of cosine is sine. Sine of 0 is 0. Sine of pi over 2.
Root 2 over 2.
Wait, what?
Never mind.
Sine of pi over 2. Pi over 2 is top of the circle. Sine is the y value. So we have a volume of 1 cubic unit. Nice and clean volume. 1. 1. Rocking and rolling.
Doing it the other way is fine.
So let's think about the discs. The discs are in a lot of ways much easier. You know, sometimes those geometric cross sections, although not extraordinarily difficult, they're a little harder to visualize. When you're just taking a region and rotating it around an axis, it's a little bit more kind of obvious. So when we have this disk set up, the area of a disk is pi r squared. And the function that you're given is always going to represent the radius if your region is touching the axis of rotation. Because that function is telling you how far away you are from the axis of rotation, how far away the curve is from the axis of rotation. So if we look at this triangle here, and we draw a vertical element at a random x, and we rotate around the x-axis, we can kind of see all these disks. Right? This thing is going to rotate around and create a disk right there. And the radius of that disk is exactly whatever the function is at that x value. Right? The radius is the function. And that's what they're showing in this formula. Pi r squared. And r is just given by whatever the function is. So in this particular case, our volume will be pi times the radius squared. Well, the radius is given by the function 2 minus 2x. So that is our setup. And they give us our limits of integration here. They tell us that that point is 1 and that point is 0. So this will be our volume. Does everybody see it? Pi r squared. So we are going to have to FOIL this out before we integrate. So we get 4 minus 8x plus 4x squared. 0 to 1. Once again, the antiderivative for all these powers of x is pretty straightforward. Plugging in 1, we just get the coefficients. Plugging in 0 gives nothing. So we end up with 4 pi over 3.
Are you worried about units on any of these?
In math, you deal with the units if they give us units, and none of these problems have any units in them. So we'll get to some. Do you like units?
Just from physics, basically.
So when we get to 6, 7, it's all about units. That's the application section. So then we'll use a bunch of units, but most of these they don't even put them in. So we don't need them.
Units squared.
Isn't this kind of tied to dimensional analysis? Like if we took the integral of volume, we would get a quantity that, I don't know what that would be.
Yeah, the units will all match with the dimensional analysis. And when we get into 6, 7, where we're trying to find the work done emptying a tank or something, we will definitely analyze the units. Because the units tell us everything when we're dealing with an application. Here the units are boring. It's just, cubic meters or whatever. But yeah, when we get to 6, 7, we'll do a lot of units. What time does this class end?
15.
15, okay.
We should go early.
Yeah, no, I think it's 5.
We should do a vote. This is democracy, right?
No! This is a dictatorship. Just be clear. Benevolent dictator, but. All right, we'll do. Oh, an exponential.
No.
Yes. Exponentials. Exponentials and logs.
So gracious.
I am going to fill in all the leaks in your boats. Okay. So we've got this exponential decay function, and that's going to be our upper boundary. That's going to give us our radius. So if we draw a vertical element at a random x, the radius of the corresponding disk. Yeah, it looks a little messy. Let's just go like that. So the disk that we're going to create has a radius of r. Do it like that.
So it's going to be from 0 to -1.
So tell me what the area of our disk is then. So how does that simplify? Everybody agree with that?
Sure.
Power to power multiply. Power to power multiply. Everybody okay with that? Power to power multiply. So that is the area of our disk. So the part that gets a little funky now is that the volume is the integral from 0 to natural log of 4, pi e to the negative 2x dx.
Is the integral, or do you just break down the negative? Actually, no, cancel.
Close. Yeah. Okay, so we talked about this at the very end of our class on Wednesday through Zoom. Zoom and Doom. When the substitution, I don't know, because I didn't know names then. Someone was asking about this at the end of the class. When we have a linear substitution, we can use a technique called reverse chain rule. In Calc 1, you would have done this with U substitution. But what we notice in this exponent is that this is linear. And so it's linear because the power on the x is a 1. So if you have a substitution that's going to be linear, so it's going to be like mx plus b, linear, then you can avoid doing U sub. U sub is at least 3 steps every single time. But if your substitution is linear, you don't need to do it. You can do reverse chain rule.
When you said x is 1, do you mean like x to the power of 1?
Yes, x is raised to the first power. Right. So it's linear if it's in that form, 5x plus 3 or something like that, raised to the first power. So what we can do in this case is we can factor out the pi, of course. And then the integral or the derivative of an exponential starts with itself. So we just rewrite the function. And if you were differentiating, you would multiply by negative 2. But since we are integrating, we divide by negative 2. So that is reverse chain rule. So reverse chain rule, RCR, and that works when the substitution is linear.
Do we need to label that stuff?
No. No. So then we just have to deal with our substitution of the limits now. So let's pull the negative pi over 2 kind of out to the front, and we'll think of just evaluating the limits in this, because constants can always factor to the front. So we're going to plug our limits of integration just into that yellow part. So this is e to the minus 2 ln of 4 minus what?
1.
Minus 1. I'll write it as e to the 0 for one step just to make sure. So in this case, the 0 matters. We had a lot of integration where the 0 didn't contribute. Here it matters. So then we get minus pi over 2. And this is going to be 1/16 minus 1. Right?
How? Can you walk through it? How?
So remember that coefficients to a log can take flight.
Oh, yeah.
So that negative 2 can move into the inside of the log and become an exponent. And then 4 to the negative 2 is 1 over 4 squared, which is 1/16. See it?
Yeah.
So the coefficient comes up as an exponent, and then the e and the ln are going to cancel. E and ln are inverse functions of each other, so they cancel each other out. And we're just left whatever is inside the log. So that's going to be a 16. OK, so then this all becomes, this is all good. That's going to become 15/16 with the negatives cancel, so we get 15 pi over 32. All right, any? OK, so let's see. Are we at the shells yet? I want to. Let's see. Or at the washers, I mean. OK, so let's go over. Roberto asked a question earlier. And I put it up here in this question space. let's talk about this for a moment. Maybe I won't write it all down because it's part of the homework. I want you to think about it. But so here we're given a drag racer that accelerates at 64 feet per second squared. So that's the acceleration. And we're going to assume that it's a drag racer. Initial velocity is 0, initial position is 0, starting at the start line. So it says determine the position function for t greater than or equal to 0. So we're starting with acceleration as a constant. And this funny drag racer is going to take off at 64 feet per second squared. And what's his velocity going to be?
64 x plus c.
So exactly. So we're going to integrate. If we do a t, it would be 64t plus c. But what's the c going to be? 0 because the initial position, the initial velocity is 0. So 64t would be the velocity at time t. And then if we want to get to position, what are we going to do?
Antiderivative.
Antiderivative again. 32t squared plus c. But that's going to also be 0 because the initial position is 0. All right. And so that'll get us through these first two questions, first two parts. And then this one says, at this rate, how long will it take to travel a quarter of a mile? So we know that displacement and distance are going to be the same, right? The car is not going to go backwards, so it's going forward. So if we do the integral, we want the integral to equal the distance traveled, or the displacement integral should equal a quarter. So then we're going to have to integrate, and we're going to have a letter in the limit of integration, and that's going to be a variable. So then we have to sort of back substitute to figure out what the t is. So we know that the integral has to equal a quarter. So if you have something like this, 1/4 equals integral from 0 to t of something like that, something like that. Right? That's going to end up being a function of t on the right, and then you would solve that for t. So think about that. We can talk more about it on Wednesday. All right, let's. Wait, you had a question. What was that question?
It was 4, but I think I might know what.
Okay, all right. We'll go with that. If you get in there and you're still not sure, just post it in here, and I'll reply to you. Question.
Like, are your health hours in here or at your office?
They're at my office because there's a class in here.
But isn't that hallway locked? Like the master teachers? Like,
No. Yeah, you go through the main entrance right there.
yeah. They keep it unlocked during my day.
Yeah. Oh, yeah.
Because you have the badge.
Yeah, not during the day.
Okay, got it.
Yeah, so you can just walk right into the main dump over right there. Yeah, there's a class in here. So we'll do
They're telling me how bad she is.
yeah, you've got the cool gadget. All right, good to see you in person. In person. See you on Wednesday. Absolutely. Thank you. Oh, totally fine. It's the first day. No. You're totally fine. Obviously, I don't know.